All right, let's talk about RAG pipelines. If you're a data scientist, you've definitely built them, and you've definitely felt the pain of trying to make sense of messy, unstructured documents. But what if I told you the answer isn't better text extraction? What if the answer is no text extraction at all? We're about to dive into a totally different way of thinking that might just make your old pipelines look like ancient history.
I know. It sounds completely insane, right? We've poured decades of work into perfecting OCR, into pulling every last character off a page. But what if that very first step, the extraction itself, is the original sin? What if, by turning everything into a flat text file, we're throwing away the most valuable information before we even get started? So, to really appreciate just how big a deal this is, we have to take a hard look at the problem we're all living with. I call the traditional method the OCR shredder because, honestly, that's pretty much what it does to your data.
Come on, you know this pipeline. We have all built this thing. We have all spent weeks wrestling with it, only for it to break on some new document format. Every single one of these steps is a fragile link in the chain, another place where errors can creep in and just silently corrupt your data. It's a house of cards.
And here's the absolute heart of the problem. What we're doing is a form of lossy compression. Think about it. We take a rich, structured document and we smash it into a string of text. All that crucial visual context, the layout of a table, the flow of a chart, the way things are positioned on a page, it gets warped or worse, completely obliterated. You're literally damaging the information before the smart part of your pipeline even sees it. So what if we could just skip that whole brittle, destructive process? Well, that's exactly where we're headed. This is the solution, and it really is a revolution. It flips that entire pipeline on its head. That's it. That's the whole idea. Seriously, instead of fighting tooth and nail to rip characters off a page, what if we just stopped? What if we treated the document page for what it actually is, an image? And the tool that makes this possible is a model called ColPali. Now, the name actually tells you everything you need to know. The poly part comes from Polygemma, which is Google's super powerful vision language model. It can understand images. The col part comes from a technique called ColBERT, which is famous for its incredibly precise search mechanism. We'll get to that in a second. And when you put the two approaches side by side, well, the difference is pretty stark, isn't it? On one side, you have that complex, error-prone beast we all know. On the other, you have a simple, direct, end-to-end system that takes in raw pixels and gives you a genuine understanding of the document, visuals, and all. Okay, so how does ColPali actually pull this off? How can it look at a whole image and find tiny, specific details? The magic here is in the architecture. It's a concept called late interaction, and this is the secret sauce. Think about standard RAG for a second. We take a chunk of text and we squash all its meaning down into one single vector. It's like making a smoothie. All the distinct flavors get blended together. ColPali does the exact opposite. It refuses to summarize. It keeps everything separate, creating this incredibly detailed, multi-vector map of the page. And how detailed are we talking? Well, look at this number, 1024. ColPali chops up every single page into a 32 by 32 grid of patches, and each and every one of those tiny patches gets its own unique vector embedding. That's over 1,000 little windows into what's happening on that page. So how does that work at search time? It's brilliant. Let's say your query is Q3 revenues. Instead of comparing one query vector to one document vector, ColPali compares the vector for Q3 against all 1024 patches on the page. Then it does the same for revenues. It finds the best match for each word independently, and then it adds up the scores. This late interaction, doing the comparison at the last possible moment, is what lets it zero in on the exact spot where those concepts visually overlap. Okay, so the theory sounds great, but where does this vision-first approach just completely dominate the old way? I'll tell you where. The killer use case is tables. We have all seen this nightmare. You have a beautiful, clean, perfectly structured table. You feed it to your OCR pipeline, and out comes this jumbled mess of text soup. The system knows the words Q2 and 4.8M are near each other, but it has absolutely no idea they belong to the same row. The spatial relationship, the very thing that gives a table its meaning, is just gone. But ColPali just sidesteps this problem completely, because it never tries to read the table in the first place. It sees it. It understands the grid. It knows that a number lines up with a certain column header and a certain row because it's preserving that two-dimensional layout in its embeddings. It gets the table for the same reason you do by looking at it.
Okay, this sounds incredible. Maybe a little too incredible. Let's be real for a second. This level of power and detail doesn't come for free. And if you're a senior data scientist, you should be asking about the trade-offs. So let's talk about the bill.
So what is the catch? 1,024 vectors for every single page. That sounds computationally expensive. And you know what? It is. This is definitely not a free lunch. But here's the really interesting part. It's not just a higher cost, it's a cost shift. You're trading one set of problems for another. You kill the unpredictable, frustrating engineering hours you spend fixing brittle OCR pipelines. In exchange, you get a much larger but very predictable vector database storage bill. So the strategic question is, where do you want to spend your budget? On developer headaches or on storage? But the story doesn't end with a massive bill. This is a solvable engineering problem, and people are already on it. The most promising idea is called token pooling. Basically, the model learns to group together redundant patches, like all that empty white space on a page. Early research shows you can slash the vector count by more than 60% and lose barely any performance. You combine that with things like quantization, and that billion vector bill starts to look a whole lot less scary. And really, this quote from Zilla's just nails it. This is the whole thing in a nutshell. We are moving from a world where what you extract is what you search to a much more powerful, much more intuitive world of what you see is what you search. So I'm going to leave you with this question to think about. All those documents we've always called unstructured or semi-structured, the PDFs, the scans, the complex reports, suddenly their structure can be perfectly understood. So as this tech gets better and cheaper, how is it going to change the very definition of unstructured data where you work? And what new things will you be able to build when that happens?